So this is the last of 3 videos that takes us through determining rate laws and some other questions using the initial rates method. Here's the data we're going to use. So we have A plus B yielding C. Again, don't worry about the stoichiometry. It's not critical for rate law determination. And so we have a fair bit of data. We can do a couple of these calculations twice if like. So you can do that if you like. I'm not going to bother. I'm going to show you once. So here are the questions we're going to answer. So A to F, 6 different questions, and why don't we get started right now. So determine the experimentally derived rate law for this reaction. So I'm going to use 3 different equations. I'm going to use these are equations 1 and 2 and 3. So I'm going to use 1 and 2 to determine the effect of changing the concentration of A. So this is what we're trying to solve. We're going to look at how rate changes based on a change in the concentration of A. In experiments 1 and 2, we've doubled the concentration of A, and as a result, the rate went up by a factor of 4. And so this reaction is second order in A. So this the exponent for the concentration of A is 2. Well, how about for B? Well, experiments 2 and 3 can allow us to look at an effect of changing the initial concentration of B. So there we go. We have not changed rate. So if we start at 1 and nothing changes, we can leave it at 1. And so what did we do to the concentration of B? We actually doubled the concentration of B. And so what must B equal? 2. Well, B must be equal to 0. So this reaction is actually 0 order in B. That is to say, there is no effect on the rate of this reaction when you change the concentration of B. So the experimental derived rate law is going to look like this. R equals K, concentration of A, squared, second order A, concentration of B, 0. Whoops, that's not a 6, that's a 0. And so we can rewrite that if we like, ignoring or leaving out the B altogether. Since it does not affect rate, it does not have to appear in the rate law expression. So 2 ways to show that rate law, but there it is. R equals K times the concentration of A squared. All right, next. What is the overall reaction order? Well, this is pretty easy now. Overall reaction order comes from the sum of the exponents, and so the reaction order is second, 2. It is second order in A, and is 0 order in B. All right, that was easy. All right, determine the rate law constant K for this reaction at this temperature. Again, all we need is one set of data and our rate law expression. So here we have it, and so we're going to rearrange that equation like we did in the previous example. So K equals rate divided by the concentration of A squared. So our rate is 0.0080 moles per liter hour. Notice this slight difference in the rate unit, moles per liter hour, not moles per liter second, divided by concentration of A squared. So that's 1.0 moles per liter squared. And so when we do the math on that one, that equals, well, 0.080 as the number. What about the unit? And again, this is where you have to be careful in your analysis of the unit. It comes out to liter per mole hour. Okay, so there's the rate constant K, 0.0080 liters per mole hour. Next, determine the rate of reaction if we have a new concentration. If now we've changed the concentrations, 2.0 moles per liter in A for a concentration of A, and we've really increased the concentration of B. But as you know, it's not going to have any effect. So there's our rate law. R equals K, A raised to the power 2. no b, so it doesn't matter what we do with our b. But now we have our rate constant k, we just calculated 0.0080. Now remember the units, liter per mole hour times concentration of A squared, 2.0 moles per liter squared. And so what we get there is 0.032 moles per liter hour. Again, if you look at the unit analysis here, moles squared per liter squared. Well, moles divides out here, we're left with 1. Liters divides out there, we're left with 1 on the bottom. So we have 1 and 1, so moles per liter hour. All right, and that should make sense to you because the rate has increased, not surprisingly due to an increase in the concentration of A. Okay, so here's the next question. If the temperature is decreased, what will happen to the value of K? Explain your answer. Well, you sort of have to just work through your rate constant, which you remember R equals K A squared. But in the face of a temperature decrease, rate is also going to decrease. So let's isolate K. K equals R over A squared. Now we haven't done anything to the concentration of A. That is still the same. So if we decrease rate, K is going to decrease. Okay? So in terms of explaining it, the value of K will decrease when T is decreased due to a decrease in the rate of reaction. So there you go, there's the explanation, and you arrive at your explanation by working through these, the rate law, the fact that T decreases, rate decreases, and how that's affecting K. Last question. If A is doubled, what will happen to the rate of reaction? If B is doubled, what will happen to the rate of reaction? We already sort of know this. If we double the concentration of A, so we increase that by a factor of 2, that's 2 squared. So if we double the concentration of A, the rate will increase fourfold, or increase by a factor of 4. If we double the concentration of B, well, nothing happens, right? Double B, no effect. B is not part of the rate law. B does not affect rate. Because it's not in the rate law. And my pen is slowing down. There we go. Okay, so a decrease in the rate of reaction of the pen writing at the end there. But those are the sorts of questions you can expect, and that concludes this video.